Preparing for a Backend Engineering at JFrog interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design a highly scalable artifact upload service? I would separate artifact bytes from artifact metadata. Clients upload chunks directly through authenticated services to durable object storage, while a metadata database tracks repository, path, checksum, size, and completion state. Upload sessions make retries resumable, and content hashes enable deduplication and integrity checks. I would publish completion events only after validation. Stateless API nodes scale horizontally, whereas storage and metadata require independent capacity planning, replication, rate limits, and monitoring. While answering, cover multi-part uploads, resumability, object storage, metadata separation, checksums, replication, authentication, concurrency control, idempotency, network failures, and observability. Explain how the design supports large files and increasing repository traffic. Question 2. How would you make artifact uploads and downloads idempotent? For uploads, I would use the repository, path, version, and content digest as an idempotency identity, backed by a uniqueness constraint. A repeated request can return the existing artifact instead of writing another copy. Multi-part sessions need durable chunk state and a completion marker. Downloads are naturally repeatable, but cache validation with e-tags prevents unnecessary transfer. I would define overwrite behavior explicitly, because idempotency does not automatically mean immutability. Make sure to cover stable idempotency keys, content digests, conditional requests, retries, duplicate suppression, partial uploads, database constraints, safe overwrite semantics, and the difference between retrying an operation and repeating its side effects. Question 3. How would you model artifact metadata and repository paths in a relational database? I would store repositories, artifact coordinates, versions, manifests, checksums, and storage locations as separate entities, with tenant ownership on every relevant row. A uniqueness constraint would prevent conflicting immutable coordinates. Indexes should match lookups such as repository plus path and checksum searches, while large manifests may use compressed JSON or normalized tables depending on access patterns. I would separate deletion state from physical garbage collection, preserving transactional metadata until storage cleanup succeeds. In your answer, discuss repository and artifact entities, versions, checksums, manifests, indexes, immutability, soft deletion, tenancy, pagination, transactional boundaries, and how query patterns influence schema and index design. Question 4. What consistency model should an artifact repository provide? For a successfully published immutable artifact, I would provide read after write consistency in the serving region, so a build can immediately retrieve what it just published. Cross-region replication may be eventual, but the API should expose availability or lag clearly. Metadata must never point to an incomplete blob, so publication uses a commit marker or transaction. Eventual consistency is acceptable for search indexes and analytics, not for dependency resolution correctness. Be sure to mention read after write behavior, immutable artifacts, metadata and blob consistency, replication lag, cache invalidation, quorum choices, user expectations, and where eventual consistency is acceptable without breaking builds or deployments. Question 5. How would you design replication across regions for artifacts and metadata? I would replicate immutable blobs asynchronously across regions using checksum verification and resumable transfers. Metadata events would carry monotonically increasing versions, allowing consumers to reject stale updates. The serving region can acknowledge publication after durable local storage, while policies determine whether cross-region durability is required. Failover needs health checks, DNS or routing control, and a replayable event log. Immutable coordinates simplify conflict resolution, although mutable tags still require explicit ownership rules. Focus on synchronous versus asynchronous replication, regional failure handling, ordering, conflict resolution, checksums, failover, recovery point objectives, recovery time objectives, bandwidth costs, and immutable artifact advantages. Question 6. How would you implement content-addressable storage and deduplication? Content-addressable storage keys blobs by a strong digest, such as SHA-256, while repository metadata maps human-readable coordinates to that digest. Before storing a new blob, the service checks whether the digest already exists, reducing duplicate bytes. I would verify the digest during upload and maintain references so garbage collection removes only unreferenced data. Authorization remains namespace-based. Sharing physical bytes must not grant access across tenants. Discuss cryptographic digests, collision considerations, reference counting, namespace metadata, atomic rights, garbage collection, storage savings, hash verification, and why deduplication must not compromise tenant isolation or authorization. Question 7. How would you design dependency resolution for Maven, NPM, or Docker artifacts? I would parse ecosystem-specific manifests, resolve direct and transitive dependencies using deterministic conflict rules, and record the selected versions. Repository priority and proxy policies must be explicit. Metadata and remote responses should be cached with controlled expiration, while negative caching prevents repeated misses. For reproducibility, lock files or resolved manifests should pin exact versions and digests. Cycles require detection, and mutable upstream tags should be treated cautiously. Cover version constraints, transitive dependencies, metadata caching, conflict rules, repository priority, remote proxying, negative caching, cycles, reproducibility, and protecting builds from changing upstream content. Question 8. How would you build a reliable remote repository proxy? On a cache miss, the proxy should coordinate concurrent requests so one upstream fetch populates the cache while others wait or receive a controlled response. I would use bounded timeouts, retries with backoff, circuit breakers, and negative caching for confirmed misses. Every downloaded artifact gets checksum validation before publication. Serving stale cached data can preserve build availability, but that policy must be visible because freshness and reproducibility can conflict. In your answer, discuss cache-aside behavior, upstream failures, timeouts, circuit breakers, negative caching, stale data, authentication, checksum validation, rate limiting, and avoiding cache stampedes during popular dependency requests. Question 9. How would you secure an artifact repository in a multi-tenant environment? I would authenticate users and services through short-lived tokens or federated identity, then authorize every repository operation using tenant-scoped policies. Storage keys should not be directly guessable, and downloads require authorization even when blobs are deduplicated. TLS protects transport, encryption protects stored data, and audit logs capture actor, artifact, action, and outcome. I would also validate paths, scan uploads, rotate credentials, and apply least privilege by default. Mention authentication, authorization, tenant isolation, repository scoped permissions, service identities, least privilege, token rotation, encryption, audit trails, path traversal prevention, and defenses against malicious or poisoned artifacts. Question 10. How would you design an artifact promotion workflow from development to production? I would promote an immutable artifact by changing trusted metadata or repository membership rather than rebuilding or copying bytes. The workflow records tests, scans, approvals, provenance, actor, and timestamps, then atomically updates the promotion state. Production deployment references the digest, not a mutable tag. Failed promotion leaves the original state unchanged, and rollback selects a previously approved digest. This preserves traceability and prevents environment-specific rebuild drift. Focus on immutable versions, metadata versus copying bytes, promotion gates, approvals, provenance, environment policies, rollback, auditability, race conditions, and ensuring production consumes exactly the tested artifact. Question 11. How would you implement garbage collection for unreferenced artifacts? I would first identify routes such as repository references, manifests, releases, retention exemptions, and active upload leases. A mark phase computes reachable digests, and a later sweep deletes unmarked blobs after a safety delay. Deletion must be idempotent and coordinated with concurrent publication, using transactions or leases to prevent races. I would support dry run reports, policy-based retention, metrics, and recovery windows because accidental deletion is costly. Discuss reachability, manifests, tags, retention policies, tombstones, race conditions with active uploads, mark and sweep, delayed deletion, leases, dry runs, and protecting artifacts still needed by deployments. Question 12. How would you troubleshoot a sudden slowdown in artifact downloads? I would begin by comparing P50, P95, and error rates across repositories, regions, artifact sizes, and clients. Traces can separate authorization, metadata lookup, storage retrieval, and network transfer time. I would inspect cache hit ratios, object store latency, connection pools, throttling, and recent deployments. Mitigation might include shifting traffic, disabling an expensive feature, or increasing capacity. I would confirm recovery with controlled measurements, then document the root cause and prevention. Make sure to cover symptom definition, latency percentiles, throughput, regional comparison, cache hit rate, storage performance, database timing, network saturation, recent changes, tracing, dashboards, and safe mitigation. Question 13. How would you design a reliable event-driven indexing pipeline for artifacts? After metadata commits, I would publish an event through an outbox so database state and event intent cannot diverge. Consumers update search indexes idempotently using artifact identifiers and version numbers. At least once delivery is acceptable when retries, exponential backoff, and dead letter handling are implemented. Events need version schemas and correlation IDs. A replayable log allows rebuilding indexes, while lag metrics and backpressure protect the system during ingestion spikes. Cover transactional event publication, durable queues, at least once delivery, idempotent consumers, ordering, retries, dead letter queues, schema evolution, replay, backpressure, and search index consistency. Question 14. How would you prevent duplicate processing in a distributed job system? I assume workers can crash after performing work but before acknowledging a message, so delivery is at least once. Each job carries a stable identity, and side effects use idempotent rights or uniqueness constraints. Leases and visibility timeouts allow recovery from failed workers, while retry limits route poison messages to a dead letter queue. I would avoid claiming exactly once unless every downstream side effect participates in a coordinated, verifiable protocol. Discuss at least once semantics, idempotent C keys, unique constraints, leases, visibility timeouts, acknowledgements, retries, worker crashes, poison messages, and why exactly once processing is usually an end-to-end property. Question 15. How would you evolve a public backend API without breaking clients? I prefer additive evolution. New optional fields, endpoints, and capabilities rather than changing existing meanings. Clients should tolerate unknown response fields, while servers validate inputs carefully. Breaking changes need an explicit version, migration guide, overlap period, and usage telemetry. Pagination must remain stable under concurrent writes, typically using cursor tokens. Contract tests and deprecation metrics reveal dependent clients before removal, and error codes should remain machine-readable. Mention backward compatibility, additive changes, versioning, semantic contracts, deprecation periods, tolerant readers, pagination stability, error compatibility, contract tests, observability, and migration communication. Question 16. How would you handle rate limiting for artifact APIs? I would apply hierarchical limits by tenant, user, repository, and endpoint, using token buckets to allow controlled bursts. Uploads and downloads should consume weighted capacity based on bytes, not merely request count. Distributed enforcement can use a strongly consistent counter service or local limits with bounded error. Responses should include retry guidance and remaining capacity. Separate pools for critical control plane calls prevent large transfers from starving authentication or metadata operations. In your answer, cover tenant fairness, token bucket or leaky bucket algorithms, distributed counters, burst capacity, weighted requests, response headers, retries, upload bandwidth, and preventing one customer from exhausting shared resources. Question 17. How would you test a backend service that manages large artifacts? I would unit test validation, authorization, state transitions, and retry logic, then use integration tests with real databases, queues, and object storage interfaces. Contract tests protect clients and remote repository protocols. Load tests should vary artifact sizes, concurrency, cache hit rates, and regional latency. Fault injection covers dropped connections, partial uploads, duplicate events, storage outages, and worker crashes. Security tests include path traversal, tenant isolation, token abuse, and malicious package scenarios. Be sure to mention unit, integration, contract, property-based, load, stress, fault injection, security, checksum, resumability, concurrency, and recovery testing, plus realistic storage and network behavior. Question 18. How would you design observability for a JFrog-style backend service? I would define SLOs for upload, download, metadata, and promotion operations, tracking latency, errors, traffic, and saturation. Every request receives a correlation ID propagated through queues and storage calls. Structured logs capture tenant, repository, operation, outcome, and size without leaking secrets. Traces expose cross-service delays, while metrics show cache hits, replication lag, queue depth, and garbage collection progress. Alerts should reflect user impact, not merely infrastructure noise. Focus on structured logs, metrics, distributed traces, correlation IDs, golden signals, artifact-specific dimensions, SLOs, alert thresholds, audit events, cardinality control, and actionable dashboards for operators. Question 19. How would you choose between a relational database, document store, and object storage? Object storage is appropriate for large immutable bytes because it offers durable capacity and efficient streaming. A relational database fits metadata requiring constraints, transactions, and predictable queries, such as repository coordinates and promotion state. A document store may help flexible manifests or high-scale denormalized reads, but adds consistency and indexing trade-offs. I would choose based on access patterns, not fashion, and keep references between systems repairable and observable. Discuss access patterns, transactionality, blob size, indexing, consistency, scalability, operational complexity, cost, backup requirements, and why metadata and artifact content usually have different storage needs. Question 20. Describe a backend incident you would expect in an artifact platform and how you would lead the response. Suppose a metadata migration causes intermittent download failures. I would declare an incident, quantify affected tenants and regions, assign communication and investigation owners, and halt further rollout. Logs, traces, and database metrics guide a reversible rollback or feature flag mitigation. I would communicate status and workarounds at predictable intervals, then verify recovery through synthetic downloads and error rate trends. Afterwards, I would write a blameless review with tests, rollout safeguards, and ownership for each corrective action. Make sure to cover detection, impact assessment, incident roles, rollback, communication, evidence preservation, mitigation, recovery validation, root cause analysis, and concrete follow-up actions without assigning blame. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.